This is Chapter 7, Problem 14. And this is the problem with the dump truck and the sand. And what's going on is the sand is falling, and it's falling 2 meters, being dropped, and then hitting the bed of the truck. And the question asks, by how much does the scale, the reading on the scale, exceed the weight of the truck and the sand at any given point? And in the question, this was the big hint, they gave you, with the 55 kilograms per second, a change in mass over time. So what are we going to do? If we want to know how much the scale reads on top of what it should read, we've got to think about what is that extra due to. Well, we're already going to be, it already says don't worry about what the actual weight of the truck and the sand is. So I don't think we really need a free body diagram. What is the extra due to? The fact that this sand's got to be stopped. Okay, its downward momentum's got to be stopped by the truck, and as a result, by the scale. So we're talking about while sand is hitting the bed of the truck, what's the extra this is going to read? Well, if we're talking about during a collision, fat app is what we're going to try to apply. So I'm going to go ahead and write F delta T equals the change in momentum. And this average force exerted by the truck on the sand up to stop its momentum, to make it so it has now a change in momentum to 0, is that upward force will also be the extra that we get on the scale. Because what is the truck sitting on? It's sitting on the scale. So the sand hits the truck and the sand move down, the scale's got to stop it. So this average force is the extra that the scale will read. So now what do we need? Well, we need delta T and we need change in momentum. Let's rearrange this a little bit since I have an M up here. So let's say F delta T equals change in mass, because we got momentum, times change in velocity. So MV, I'm going to make those both deltas. Typically our mass is not changing, but this is a case where our mass is absolutely changing. Now I'm going to rearrange because we're pouring in sand. So now I'm going to rearrange this equation. So I'll have delta M over delta T times delta V. So I've just divided both sides by delta T. And now there is our, I think I accidentally put a dot there. I think it's 55. Yeah, there's our, that shouldn't be there. There's our 55.0 kilograms per second. So we know that number. So now the big question is, what's our change in velocity? And remember, this is average force, time of the collision, change in momentum for the collision. So this is the change in velocity as a result of the collision. Well, eventually the sand's going to come to a stop. So I'm going to expand this out a little bit more. So delta M delta T times V final minus V initial. Our V final is going to be 0 because the sand will come to a stop. Now the question is, what speed did the sand hit at? And that's a much easier question to answer. If this is okay, you're in great shape. If this isn't, come in and see me. We can talk more about why it's like this, and I can expand on those ideas. But now my big goal is figure out how fast did this sand hit at, because that'll be my V initial to plug in here. So I'm going to do a completely separate problem. I've got some sand, and it's dropping 2 meters. And I want to know what's this velocity right here. I'm just going to call that V2 to avoid confusion here. And this will be my new, which I wouldn't have done. I'll call this V1. So here's my V2, here's my V1 for this new problem. Now it's being dropped. You could do this with motion equations, because it's probably in free fall, or it is in free fall, or you could do this conservation of energy. I'm going to go ahead and use conservation of energy because it's quicker. So ME at 1 equals ME at 2. Call this a height of 0 right here. So at the top, if it's being dropped, it's all potential. So PE at 1. At the bottom, height is 0. It'll be all KE. KE at 2. So MGH1 is 1/2 M V2 squared. The M's will cancel out, and that's good because I have no idea what the mass is of some of this sand. I know how it's changing when it hits, but I don't really know the mass of the sand at any given point for a certain amount. So it's good that that canceled out. And now I'll get my V2 equals square root of 2GH, and that's stuff that I do know. So V2 will be 2 times 9.8 meters per second squared times our height of 2 meters, square root of all that. And let's actually get an answer for this. Let's see here, where's my calculator at? There we go. So we got 2 times 9.8. Oh, I swear I'm pressing buttons. It's not working. Let's kill that and try it again. 2. Oh no. My calculator's busted. Okay, I'll carry that stuff through when we'll use 10. So let's go ahead and call this 10. So 10 times 2 is 20, times 2 is 40. So I got square root of 40 here, meters squared per second squared. And I could approximate, but let's just go ahead and leave it like that. And then we'll move up here and plug in. So my F will equal, my delta M will be 55 kilograms per second, times my negative of that, which is square root of 40 meters squared per second squared. And the negative makes sense, because my final answer here, I'm going to get some negative force. Well, if you think about it, okay, I'm calling, oh, wait a minute, let me be consistent here. I'm actually calling, if I leave this as a positive, I'm calling down positive. I'm going to go ahead and call down positive so that my V2, this is a positive number. When I come back in here, velocity, I got to make sure I add the sign if necessary. I've called down positive, so I'm subtracting that positive number, and now I will get a negative for an answer, and that makes sense because my force is going up. If I call down positive, that's a negative force. That's the extra that the scale will read. The magnitude of that. So the final answer will just be absolute value of whatever 55 times the square root of 40 is. Let me see if I have another calculator app on here. I'm sure I do. Oh, there's Amazon. That's great. Let's see here. Let's go into the apps. I'm sure there's another calculator. Okay, so if I can use this, we'll see. We're trying to do the square root of 40. So square root of 40. That looks about right, because 7 would be 49, right? So 6.3 something times 55. So 347 newtons. So the overall answer will be 347 newtons. And let's check that one. Oh, I think that's right. If not, I don't have the key handy. If not, this is probably, yeah, that should be right. 55 times that, that should be fine. If it's not right, the only mistake will be right here at the end with the algebra, the substitution. Again, if you need help on this part, come in and see me, because this, I think, we're probably all right. And if you didn't like this method, just use motion equations to get your V2. That's it.